Okay, so now I'm going to move on to another example where we have, instead of one sample, we're comparing two groups. We're doing a two-sample hypothesis test. Still going to be a t-test, but it's going to be two samples this time. Okay, so now let's read this example here, which is a teacher wishes to test the notion that two versions of exams are equally difficult by randomly assigning one version to each student with equal probability. Teacher found that the average scores in the exams were so different, not likely to do the chance. They may want to award extra points for the students who took the more difficult exam. Okay, let's say that, for instance, that this is a school-wide exam. And in order to test the two versions of the exam, the teacher gave a group of 30 randomly selected students version A, and she gave a randomly selected group of 27 students version B. As it turns out, that the average result was 79 on the first exam, and it was 74 on exam B. Now, she calculated a standard deviation for those scores of those 30 students, and a standard deviation for the scores of these 27 students. Well, gee, okay, we don't know. See, now we don't know what the entire school would score on this exam, and we don't know what the entire school would score on this exam. We're dealing with just these samples of these two, and we're really interested in, is the true mean for the entire population really different than the true mean for the entire population that took exam B? Okay, so we're going to have to test this hypothesis. First, we're going to phrase a hypothesis. Okay, H null. Well, now we have a two-sided test, right? So now with a two-sided test, we're comparing two means. We're testing whether the mean for group A is equal to the mean for group B, people who took test B. And what's our alternative? Okay, well, alternative hypothesis is that the scores are different. The students would have gotten, the average students of this school would have gotten different scores on these two exams. Okay, in other words, the mean for group A does not equal the mean for group B. Notice I'm not putting X bar, the mean X bars in here. I'm putting the means because that's ultimately what we're interested in, the means, not the population means, not the sample means. That's really what we're trying to prove. Okay, so now notice also, again, this is a two-sided test, right? I didn't make a judgment as to which one of the exams was better or worse. I just want to know, are they different? Okay, so for at the moment, anyway. So I'm going to say, well, what's the level of error that we're willing to accept? Did they mention here? It doesn't look to me like they chose a specific level of error. Let's say that we're willing to accept a type 1 error alpha, a type 1 alpha error of 0.5 or 0.05 or 5%. 5% chance of being wrong if we reject the null hypothesis. Okay, so now let's see what we wind up with 5% chance of having results this different if there's really no difference between these two. Another way of phrasing that. Okay, so let's test this now. Okay, well, first, what are we going to compare now? It's going to be, instead of mu minus x bar, it's going to be x bar 1 minus x bar 2, right? Because we don't know that. So we're going to need x bars. X bar for group A and x bar for the group that took the other exam. X bar B. What else are we going to need to know? Well, we're going to need to know the standard. We're going to need to know the standard deviation for group A. And we're going to need to know the standard deviation for group B. What else are we going to know? We're also going to need to know standard error. Okay, we're going to have to calculate a standard error. But I can see a complication here. We have a standard deviation for group A and a standard deviation for group B. And my goodness, they're different. They're not exactly the same. But whenever you take a sample, you don't expect these ever, even if the standard deviations of the two groups, or two populations that these groups are drawn from, are the same. And in fact, they're really the same population, aren't they? Right? Same group of students, just randomly assigned different tests. It seems to me likely that standard deviation is going to be both same for both. And in fact, one of them a little bit lower, but it's not, say, 2 or 3 times larger. They're fairly in the same ballpark, I'd say, right? So I think the standard, but now which of these standard deviations am I going to choose that represent the population standard deviation, which I need to calculate my standard error? Which of those should I use? Well, we have to make an assumption here. One of the things I could say is maybe I'll just pick something in the middle. Well, there's a problem with that. The sample sizes are not equal. So if we did that, we'd be underweighting the larger sample, wouldn't we? Okay, which would be more representative, which would hopefully be a little bit more representative of the population standard deviation. So we don't want to do that. So we need a way of combining these two standard deviations into a single standard deviation we can use to calculate our standard error. Okay, so that's going to require us to calculate a pooled standard deviation. And our justification for doing that is that, well, they're drawn from the same population. They look like they're pretty equal. And in fact, the fact that we can combine these two gives us a little bit of an advantage because that might give us a bigger sample size for the standard error and maybe a bigger estimate of what the true standard deviation is for the whole population. So I'm going to try and get to this sheet that we had made up before. Okay, and you'll notice that on this sheet that we calculated that when we were working, we came up with a few different scenarios when we're comparing two populations and doing hypothesis testing. One is that the standard deviations are assumed to be equal, which is what we're doing in this case. Another is where they're assumed not to be equal. And a third where we're dealing with proportions, which is kind of a whole new ballgame when we're comparing two proportions. Okay, so now I'm going to put this out of the way. No, I'm not going to put it out of the way. I'm going to take a quick look at it. Okay, so how are we going to calculate this? Well, what we're going to do is we're going to calculate a t-score just like we did before. Okay, except this time we have two means, x bar 1 minus x bar 2 instead of a mean and a single sample average. Okay, so we're going to, the distance that these two are apart, the difference between x bar 1 and x bar 2 divided by the standard error is what's going to give us the number of standard errors apart that these two are. And we hope that it's going to exceed our t-score, the number of standard deviations apart, standard errors apart, that we require to be able to reject the null hypothesis at the level of certainty that we want. Alpha is 0.05. Well, down here, see this S1's really, that should be a P in there. SP squared, the pooled standard deviation. We actually have to calculate a pooled standard deviation to finish this formula. We know our means. We don't know what this is because we need a pooled standard deviation. This S squared and this S squared are the same value, but they're the pooled standard deviation. Pooled standard deviation is equal to, and there's a calculation for it. See, basically, it's weighting the two standard deviations so that we're fairly distributing, we're fairly calculating the overall standard deviation as something that's really representative of the difference in the sample sizes. Okay, so we're going to calculate that for our particular situation here. And I'm going to go back in and start to fill in some of this stuff. Okay, so what is our, I'm going to get rid of this for now. Okay, what is x bar A? Let's go back to the problem. Okay, the mean for the first group is 79.4. Mean for the second group is 74.1. Okay, and let's see, the standard deviation for the first group is 14. Standard deviation for the second group is 20. Okay, and now I'm going to calculate my standard deviation pool. And what is my standard deviation pool equal to again? I'm going to pull this up and kind of put it on the side here. It's going to be equal to, let's see if I can pull this off in here. You could use a calculator for this. You could break this up into a number of different calculations. Maybe I'll even do that. Okay, and I noticed before I even do the calculation, I need S1 squared, not S1, but S1 squared. So I really need to square this, so I'll have it ready for this formula. So this is going to be equal to, S1 squared is going to be equal to 14 squared, or 196. S2 squared is going to be equal to 20 times 20. It's going to be equal to 400. So that's S1 squared and S2 squared. And SP squared. Okay. And what else am I going to need? I'm going to need the sample sizes, which I already kind of know, but let's put them down here. Sample size 1, sample size A is equal to 30. And and sample size B is equal to 27, as I recall. Okay, so now let's go to work on calculating our pooled standard deviation. Our pooled standard deviation is going to be equal to, I'm going to do the top part of this first. It's going to be equal to the square root, parentheses, of, let's see, n minus 1. N minus 1 is 29 times the S1 squared. Now, you probably might remember that the square of the standard deviation is the variance. That's how we got the standard deviation, is we found the square root of the variance. Okay, so that's going to be equal to, square that's going to be equal to 196. Okay, plus, let's see, the other group, N2, or group B, is going to be equal to 26, n minus 1 is 26, times the S2 squared. S2 squared is 400. Okay, and okay, so I'm going to put a parentheses around that, and that whole top, and I'm going to divide by, well, now, what is this going to be? N1 plus N2 minus 2. Well, N1 is 30, N2 is 27, so this is 57. Minus 2 is going to be 55. Okay, I'm going to put parentheses around this whole thing so we find the square root of this whole function, and it comes out to be 17. Our pooled standard deviation is 17. Notice it's in between 14 and 20, kind of what we would have expected, right, for our pooled standard deviation. We'd expect it to be between those two values somewhere. Okay, so now I can go ahead and calculate what my t-score is. Well, this gets a little complicated, doesn't it? I got, now when I got calculated my t-score, I don't have a standard error yet. I just have a standard pooled standard deviation. Again, this formula was drawn from another place. So that is really SP squared and SP squared. Okay, so I need the square of my pooled standard deviation, okay, squared. Okay, that's going to be equal to 17.1 times itself, okay, which is 292. So now I'm going to calculate my t-score in two segments here. First thing I'm going to do is take mean 1 minus mean 2. Okay, it's 5.3. And then I'm going to calculate that's the numerator. I'm going to calculate the denominator. It's going to be equal to, let's see, it's going to be equal to the square root of, and let's see, going to get a little sticky here, S1 squared, which is that, a standard deviation pool squared, which is that, divided by the sample size 1, which was 30, right, plus S2 squared, with S pooled squared again, right, divided by the sample size 2, which is 27. And I'm going to close parentheses there. Let me just take a quick look at that and see if it looks like that might actually work. It's going to do this first, then add, and then find the square root. I think it's going to work. Enter, and I get my denominator is equal to 4.53. Okay, so let's calculate our t-score. T-score is going to be equal to the numerator, x bar a minus x bar b, divided by my standard error, and that comes out to a t-score of 1.16. Well, I know in order to prove this with 95% certainty, and now degrees of freedom we're going to use here is n1 plus n2 minus 2, same thing we used before, which is going to be 53 degrees of freedom. And so the closest thing here is, say 50 is going to be, I'm going to need for alpha equals 0.05 to 2.5% either tail, right, it's going to be roughly, the t-score I need is going to be equal to 2.009, right? And the t-score I actually calculated was far less than that. So I did not exceed my critical p-value for the distance between these two means for me to reject the null hypothesis. So again, this is another example where I failed to reject the null hypothesis. And so had the t-score come out to be 2.1 or 2.7, we would reject the null hypothesis and accept the alternative hypothesis. Okay, so now you could also run into situations where we might tell you that we don't want you to assume that the standard deviations are equal, and you would have to use a different set of formulas for that. In this case, notice this is different. You're not using the pooled standard deviation. You're using the standard deviation squared for the first group and standard deviation squared for the second group. Another complication is that it's calculating the degrees of freedom for unequal variances based on a very complicated formula. Sometimes to save time as kind of a first try, we will short circuit that and instead use a shortcut where the degrees of freedom we're going to use is going to be the smaller sample size of the two groups, -1. But that's really a super conservative approach. And the best way is to actually solve this formula, or even a better way is use SPSS and have it solve that formula for you automatically. But this tedious formula is the way we calculate the degrees of freedom. So we'd be doing the same process, except using slightly different formulas for the equal standard deviations, not assuming equal versus standard deviations are equal. Okay, and lastly, we sometimes wind up with situations where we're doing the same thing for proportions. Now, I just want to quickly go over at least one problem with proportions, and I think the first or second one is the one that I did earlier this morning. Okay, here we go. Okay, I'm going to go ahead and do that right now. Confidence interval, and tomorrow maybe we'll get to doing a hypothesis test for proportions as well. Okay, okay. So now, Time magazine quoted a poll performed of 1,000 Americans, of which only 4% said that they were. I haven't done that one yet. You know, I'm looking back here to make sure I haven't done that before, because this is my second time through in an hour doing the same stuff. So I don't remember if I did it this morning or first session or second session. But anyway, okay, here we are. I haven't done it, I don't think, for this group. So our proportion here of Americans that are deja vu. Our proportion of Americans that say they are vegetarian is 4%. So notice that this is a sample of 1,000 Americans. I don't know what the real proportions of Americans are, P, right? I don't know what that is. I'm using this sample to help me to predict what that might be, or where range it might fall into. What I do know is P cap. Very often put a little cap on top of that P to make it represent a proportion of a sample, not of the population. Okay, so the proportion that I know is 4%, 0.04. Okay, that proportion, 4% of the American population, of the Americans in this sample, sample size is 1,000, sample size is 1,000. That's relevant also. Sample size 1,000 tells us that they are vegetarians. Well, I don't know what the real true proportion is in the population. What I do know is this 1,000 said 4% of this 1,000 said that they were vegetarians. So, in order to find the confidence interval for the true proportion of the entire American population that are vegetarians, I need to have a range in which I have a margin of error around that 4%. So how do I calculate that? Well, in order to calculate that, I need a standard error. Well, we know when we had a regular sample, we took standard deviation divided by the square root of n, and so on and so forth. Well, for proportions, the way we calculate it, this is equal to p cap times 1 minus p cap, right, over n, and then we take the entire thing. I'm going to have to put a space in front of this. We put the entire thing, right, take that entire calculation, right, take that entire and find the square root of it. The square root of p cap times 1 minus p cap over n. Entire thing on the square root sign. Okay, so I'm going to calculate that here, that standard error here right now. I know what p cap is. I know what 1 minus p cap is going to be, and I know the sample size. So the standard error for this sample, this repeated samples of size 1,000 from this population, we're estimating the standard error to be equal to, okay, it's going to be equal to the square root of, well, let's see, 0.04 times 0.96 over the sample size, which is 1,000. Okay, so it's going to do that and then divide by that. I want to make sure it does the square root of the whole thing, so I'll put another parentheses around here. You can do this with a calculator if you're not comfortable with Excel, or you could do this in two groups. You could just do the resolve that 0.04 times 0.96, and then divide it by 1,000, then find the square root of it, do it in 3 steps if you want, just to make sure. You'll find it, and that's what my standard error is 0.006. Okay, now, in order to calculate my confidence interval, what is my confidence interval? Just like before, with x bar plus or minus some value times the t or z score times the standard error. I'm going to do the same thing with my proportion. It's going to be p cap, right, plus or minus. And what is it going to be plus or minus? It's going to be plus or minus some value, either a t score or a z score. I queried the students before, and most of them realized that, gee, that has to be a z-score. There's a couple of reasons for that. One is that we're dealing with a large sample size. Okay, and one of the rules that we have, so that's going to be a z-score for 0.05, for a possible error of 0.05, times the standard error. Okay, alpha is 0.05. Okay, or alpha over 2 is equal to 0.025. We're not worried about that right now. Okay. I'm not just worried about the z-score. Okay, so at any rate, I don't want to confuse you with that right now. So let's take that, especially since I can't type it very well here. It's easier to write it than to type. Okay, so we're going to use the z-score instead of the t-score. What's our justification for that is? Well, one justification we have, or the major one, is we're dealing with a large sample size. Well, you may say to yourself, well, what happens when I have a proportion with a small sample size? Well, that's not really ever going to happen, because one of the assumptions that we're going to make whenever we do an analysis, a confidence interval hypothesis test with a proportion, one of the rules is that that sample size can never be smaller than 30. Okay, so we're never going to have a really small sample size. The other assumption we're going to make is that not only is the sample size never going to be smaller than 30, but both of the groups, remember this is the binomial, right? So you have people answering the question, are you a vegetarian? Are you not a vegetarian, right? They only have two choices. Well, either one of those two groups is not going to have less than 15 people in it. So the overall, you need at least 30 people in your population, and you really need more than that because you got to make sure that neither group falls under a population of 15. So let's see what we got here. 4% of 1,000 is 40 people. And the remainder that say they're not vegetarian, well, that would be 960 people, right? So both of those are over 15, and the total is over 30. So we satisfy that requirement. So we're never going to use T for a proportion because we're always going to be working with samples that are large enough to allow us to use Z. Okay, so let's calculate this. Okay, so what's this going to be equal to? It's going to be equal to P cap, right, plus 1.96, which is what we're going to use for 95% of alpha is equal to 0.05, times the standard error, and p cap minus 1.96 times the standard error. Okay, so I'm going to go ahead and calculate that. So that's equal to 0.04, right? Okay, 0.04. I'm going to do minus first. Times 1.96 times my standard error, which I calculated here. That's going to be 0.027. Excuse me, let me go in there and just change that. I'm just doing it this way so that like the first number I get is a lower boundary and the second number I get is a higher boundary. Okay, my upper boundary is going to be equal to 0.04 plus 1.96 times the standard error, which is 5.2. So the sample results show that 40 out of 1,000 people said they were vegetarian, 4%. But that is only an estimate, that 4% only an estimate of the population proportion that are vegetarian. Now I know that I can be 95% certain that between 2.8 and 5.2% of the population are vegetarians. Have a little bit more grasp of what the real population mean is likely to be. Now notice I didn't round anything until I got to the very end when I said 2.8 versus 5.2. And the reason for that is that if I round any of these other numbers before I do the calculation, then I'm taking square roots, I'm multiplying, and so on and so forth. I'm increasing my error because I'm basing it on rounded previous results. So I try and avoid rounding until the very, very, very end. Okay, so that I think is something that you should keep in mind. And remember, again, this is okay. If we had wanted a 99% confidence interval, this number, a z-score for 99% confidence interval, would be 2.58. So we would make this margin of error. This is sometimes called the z-score or t-score times the standard error, sometimes called margin of error, because you're adding it and subtracting it from the mean. Okay, that's your range. Like in a election, you have 46% of the vote plus or minus 3%. So this would be the 3% part. Okay, I'm adding and subtracting this. It would have been 2.56. So it would have been a wider range, bigger range of numbers. So I would have added and subtracted more. So this would have been further apart, these two numbers, if I wanted to be 99% certain that I captured the population mean. If I didn't need that level of certainty and I made it 90% certainty, it would have been 1.64, which would have been a smaller number I'm subtracting times standard error, smaller number I'm subtracting and adding to the proportion from my sample. And it would have been a narrower range. Narrower range gives you a smaller, lower level of confidence. Wider range gives you a higher level of confidence. And remember, the other thing that influences this is the sample size. If the sample size is bigger, your standard error becomes out to be a smaller number, so that also decreases the width. So the level of confidence that you want, the higher level of confidence, 99%, so on, the wider your confidence interval. The lower level of confidence you're willing to accept, the narrower you can make that interval. The larger your sample size is, the smaller your sample size is, the bigger the standard error becomes because you're dividing by a smaller number. So to also small sample size, smaller and smaller sample size make that confidence interval stretch out also. Okay, so that's pretty much what we covered. And as I mentioned to the guys that saw this first time around on Saturday morning, we're going to do this again tomorrow on Sunday. And if you email me, if you have specific problems you want to go through or something that you want to review or something like that, email me and I'll make sure to cover tomorrow morning when we meet again. Okay, I'm sorry I had to redo all this. I'm doubly sorry that I had to redo all this. But I think I covered basically everything that we did in the earlier session. So you haven't missed anything if you weren't able to tune in on Saturday morning. And good luck on the test if you don't make tomorrow morning session, and I don't get to speak to you until Monday. Or hopefully I'll see you tomorrow. Okay, so see you guys.